It looks like e to the x. Do you agree with that? So if you wrote the general term, what would that be? It would be the sum from n equals what, 0 to infinity of what? 2 to the n over what? N factorial. I think that's right. Plug in 0, that works. Plug in 1, that works. Okay, excellent. So what do you do next? Any ideas? Any ideas? I can sink it.
What I did was I set.
Yeah, exactly. So this is, it's something like this, right? So another way to write that would be, first of all, what is e to the x? If you want to expand it, what is it?
It's like 1 plus x.
You need to know this cold. This has to be automatic. Be confident. What is it?
X.
X. Just 1 plus x. Okay. 1 plus x plus what?
Plus x squared over 2 factorial.
Yep.
Plus x cubed over 3 factorial.
Yep.
Etc.
Correct. Nice. So therefore, what is e squared? 1 plus 2 plus
4 over 2.
2 squared over 2 factorial. I'm just doing it out. Plus 2 cubed over 3 factorial, right? Is that what you have right there?
Yes.
That is what you have. So what does this equal?
X equals 2.
This, no, not x. This whole thing. What does this equal? This is just e squared. That's all that is. That's all that is. Like, what is e to the x? Oh, you plug in 2 and you get that exact thing. So what is it? E squared. There it is. That's all it is. So each one is very similar to that. Each one is very, very similar to that. Does that kind of make sense? Like, what does it look like?
Looks like sine.
Yeah, it looks like sine of x. When what? X is what? Yeah. Pi over 2? Really? No, it's just 1. Like, what is sine of x? Tell me what sine of x is. 1 minus x over x cubed over 3 factorial, right? Plus 5th over 5 factorial, right? So what do you plug in for x to get this? 1. You plug in 1. So what is the answer to 36?
Sine of 1.
Sine of 1. So the answer to this is sine of 1. Now what about 37? What does 37 look like? 37. Looks like a geometric, but which one is it supposed to? It looks like 1 over 1 minus x. Do you remember what that equals? What does 1 over 1? 1 plus, this is the easiest one, right? And it's only convergent for certain x values, right? Because it blows up otherwise. What's the x value?
Negative 3.
Wait.
What is the x value?
Oh, yeah.
No, it's negative.
What is it?
Negative 3.
We have negative 3? 1 over 4?
X, no, it's 1. X is 1/4.
Yeah, it's x is negative 3.
So if x...
Wait, do you want it?
X is 1/4.
Oh,
Right.
You
put it.
What do you plug in for x to make...
There,
Yeah,
over
you're
there.
looking not... You're plugging it in here on this side, right? So what should x be? 1/4, yes. Don't look into it too much. You're like, what's the answer? What is
Oh,
it?
yeah.
It's on the right side. You're looking to make the right side look like it, right? Not the left. The 1 over 1 minus x is just what you're trying to make it. So therefore, when you plug in 1 over... What does this equal? 1 over 1 minus a quarter. Yeah? Yeah. 4/3. You're like, 4/3. I love that trailing confidence. The answer is 4/3. It's like trying to get me to fill in the blank. Like,
I thought
huh?
it was right, but then considering
Yeah.
how we all
Crashed and burned on the first one. That's okay. No, it's okay. Collective non-confidence is bleeding into you, Molly. That's good. That's excellent. Like, if they asked you to like find this right here.
No.
Oh, okay.
They just gave you the first part, and we're like, how far does this go? Like, is this like n equals 1?
Oh,
Is
she's
this
saying,
n
like-
equals 2?
Go ahead. Yeah, I'm
She's
trying to
saying,
understand.
So in the formula, the first value is like f of x.
Yes,
F
f of 0 if it's centered around 0.
So
Yeah,
like
yeah,
the
yeah.
second one's f to like f prime of 0.
Yep.
So she's saying that if it's saying go to like
Oh, I think I understand. Let me see.
how many values?
You have to be. You have to look at what they're specifically asking.
Okay.
So, for example, one way they could ask it is, please list the first 4 non-zero terms of the Taylor polynomial, and you have to go as far as you need to get 4 non-zero terms, right? But let's say they asked you write the 7th degree Taylor polynomial for sine of x. That would go to x to the 7th, right? But what happens if I said go to the 8th degree Taylor polynomial for x to the of sine x? It would still be x to the 7th because it would be plus 0x, right? Because the odd powers aren't there for sine, right? That's annoying. Yes, I understand what you're saying. Like, you go as far, you have to look at very specifically what they're asking.
And if you have one that's like
Here are the building blocks. Here are the basic building blocks. These need to be automatic. Might take a little while, but they need to be automatic. What are some other ones that so far you know you're going to have to memorize? For example, 1 over 1 minus x. You'll need to know that one.
ln of x.
ln of x is another one. What else? There's another one.
Binomial series.
Yeah, 1 plus x to the p. That one's going to be way more popular than you think it's possible. Like that one's going to be hugely popular because here's the thing. You can use it for any value of p. Fraction, decimal, works really well. So let's say I asked you, what is e to the negative x squared? Where do you plug in negative x squared? Wherever x is. You literally just plug it in. That's it. And then you simplify. That's it.
Sort of stumped us on that.
Yeah, you're like, how do I do? Like, nope, don't need to rebuild it. Don't need to rebuild it. You can just do direct substitution. Remember, you can do this direct substitution. It's super helpful. The challenge is going to be crafting, sanding, and massaging things to be in the proper form so that you can do direct substitution. This is pretty straightforward. It's about as nice as it gets. What about something like this? What does this mean? Well, could you just call it y instead if you wanted to? Yeah, and then let y equal anything you want, and then it's just direct substitution. So what about something like this? Is this close to something we've known before? Is that close to one of them? Yeah, so first you think it's arctan, right? But we don't really know anything about the Taylor expansion of arctan, right? Not so much. But what is it really close to? 1 over 1 plus x squared is equal to 1 over what?
1
minus negative x squared, right? What is that really close to? We know what the expansion is for 1 over 1 minus x, right? What is that? 1 plus x plus
x squared.
Right? So another way to write this, just to be nice and clean, we could say, what's 1 over 1 minus y? 1 plus y squared plus y cubed, etc., right? So let's let y equal what? Negative x squared. So therefore, what does 1 over 1 minus negative x squared equal? 1 plus negative x squared plus negative x squared squared plus
Negative x
squared cubed. Could you simplify that? Sure. It's going to be 1 minus squared plus x to the fourth.
Minus x to the 6.
Is it minus? Yeah, it's minus x to the 6th. Right, exactly.
And then I go to the plus x.
Yeah, there you go. You did it. But the point is, you need to notice that what is it really close to? One of our building blocks. It's really close to one of our building blocks. Well, it keeps going. Let's do another one. Let me see if I can actually find it. Sometimes I get lost in the zooming. What about this one? You're like, oh my gosh, a trig inside an e? Well, what is that really close to? What is e to the x equal to? 1 plus x plus
X squared is
2 factorial plus x cubed over 3 factorial plus x to the 4. You can keep going as long as you want. Yay, exciting. But in this case, what are we going to let x equal? Sine of theta. So what do we get? E to the sine of theta is equal to 1 plus sine of theta plus sine, yeah, you can say theta squared. Yeah, either way is fine. I'm doing it more explicitly. That's fine. Sine of theta cubed over 3. Yay!
3.
Factorial, thank you. Yes, Molly. This is a little different. It specifically says find the Taylor series about x equals 0 for that from the series 1 over 1 minus x. So our first step is to make this look like that. It almost does, right? What do you think we have to do to this first? What do you think you have to do to that first? What? No. We're in big kid land. Don't take no square roots, don't square stuff unless you absolutely have to. You generate false solutions. What do you have to do instead? It's really straightforward. It's an algebra 2 maneuver.
Do we expand?
What?
Do we expand?
Expand it. Yeah, so what do you get? 1 over what? 1 what?
1 squared.
2x plus x squared. And we want it to be in this form, right? So how could we make it look like that? 1 over 1 minus what?
2x plus x squared.
Close. Minus x squared. Do you agree we haven't changed anything? So in this case, where do we plug this in? We plug that in for the expansion for 1 over 1 minus x would equal x. So we know that 1 over 1 minus y, what does that equal? 1 plus y plus
Y cubed and so on.
etc., right? So where do we take those? Yay, we just plug it in for y. So what do we end up with? 1 over 1 minus y is equal to 1 plus 2x minus x squared plus 2x minus x squared squared plus 2x minus x squared cubed.
So you just
Do you agree with that? Is that good? Yeah. Another way to think of it is the following. If this is true, if two things are equal, can you square both sides? If two things are equal, can you square both sides? Is it still a true statement? If a equals b, does a squared equal b squared? Yes. If 7 equals 7, does 7 squared equal 7 squared? Yes. If two things are equal, can you square both sides to still have a true statement? Yes. Okay. So if this is true, could we square both sides?
Yeah.
Could we? So, for example, if we know that 1 over 1 minus x is equal to this, not x squared. If 1 over 1 minus x squared is equal to this, what could we do to both sides? Square both sides. And what do you end up with? 1 over 1 minus x squared is equal to this thing right here. Is that actually, so what have you now actually proven? You've proven that this is equal to what? That. It's pretty cool. It's pretty neat. One's direct substitutions, one's just square both sides. But don't square root things. If you square root things, you can cause false solutions. Be very careful. Be very, very careful. But you can build in different ways. You can build in different ways. So everybody, why don't you find a piece of the board with somebody else and try this one for me. This one's a little different. This one's a little different. Try that one for me. With somebody else, everybody. With somebody else, not alone.
Here we go. Find the Taylor series for x. Let's see, for part. Well, that looks familiar. That's the derivative of y tan.
First of all, what does 1 plus, I'll give you one hint. What does 1 over 1 plus x squared equal? Do that first. And do it. And what does 1 over 1 plus x squared equal in terms of a series? Expand 1 over 1. Don't erase that. That's good so far. Expand that for me. Okay, everybody, do it the way they're asking you to do it. They're saying, find the Taylor series for arctan from the series 1 plus 1 over x squared. So where are you starting?
Yeah, so then this.
Stop. You're hurting yourself. What does that equal in terms of a series? Do it for me. 1 over 1 plus x squared, what does that equal?
So like it's just over. So then you just need to do.
Yeah, but in terms of the series, it's just one.
Here, there.
In the terms of a series, that's just a piece of.
But that does make sense. It's
Not
not
Okay,
first,
so
and then you go back.
we just did this one. So what is it?
It just made so much
Molly
sense.
gets the credit for this one.
You see what I mean?
She understood.
So
you have two things-
you have two things that are equal, right?
It's
Yeah.
in this form.
So what did you do to both sides?
So this is the one, so it's minus minus.
Wait, what did you say?
How did you turn 1 over 1 plus x squared into?
Into.
No. So you have 1 over 1 plus x squared is equal to that. I agree with that.
Oh, yeah,
That's
you just
correct.
subtract, you just move it.
No.
This was the derivative of arctan.
So if you took the derivative, that is the derivative. So how do you turn it into arctan?
Oh, you took the antiderivative.
Yes. If you take the antiderivative of one side, you have to take the antiderivative of
The other side.
yes.
Oh, I see. So let's expand the series
Yep,
from 1
good.
plus
What does this also?
How do you?
Go backwards. What does this also?
This is the. Is this? Was that equal to, or is that the
Do you
derivative?
want the antiderivative?
So how do you
Is
turn
this the derivative of that, or is that what it's equal to?
How do you turn it into what's the operation?
Oh, okay.
Integrate.
But the derivative.
So if you integrate this side, what do you have to do?
So if this is the derivative and that's the derivative, to get it back to that, you would take the antiderivative.
Yes.
I don't think that's.
So we take the, wait a second, hold on.
We just
No,
did
we
this
can
one.
take the antiderivative.
Yeah, what is that extension?
Okay, so
What does it look like?
we take
1 over 1 minus
so write that
negative x squared, yep.
And then,
Yeah, so we take the so write that out again, and then we'll take the antiderivative of that. Yeah. So do what we did. Like write out the series. Write this out in terms of a. Just series right out, man. Yeah. What I did. Yeah. Just do what you just did.
Erase it.
I don't know. That's what I was doing. I was like, what do you do? Yeah. There you go.
5 times 2.
All right. Okay. That's good. Now we only need dot. So now it's 1. Yeah. X. Yeah. Negative x. And now we take the antiderivative of both sides.
So
Yep.
if we take the derivative of the integral.
Dot, right?
It made more sense to me.
Good old integral.
Here we go.
X, so 1 is x, we know that. Baby steps, that's an x. What is that? We add 3 to that, divide by that. So x to the 4th. So we add, that's 5. To the 6th. What?
Yeah, so plus.
Wait, 1.
Oh, no.
Those two multiply together.
Yeah, there is no.
There's always.
Yeah, that's 6. Yeah. Yeah, because
Although it makes sense
Why are you proving this
in my
out?
head. What we did.
like x to the, because this is 6, and then we.
Would it be this?
So it'd be.
Oh yeah, I'm sorry. I'm
Okay, sit down, everybody. Sit down. Oh, good. Good. Nice.
All right, that's
Yes. So what was step 1 on this one? Oh man, I left that recording the entire time. Okay, so we know that 1 over 1 minus negative x squared, right, is what you're making it look like. You're pressing it into 1 over 1 minus x. So what did that turn into? 1 plus negative x squared plus negative x squared cubed plus what? Negative x squared to the 4th, dot. So you simplify that and you end up with what? 1 over 1 plus x squared minus x to the 6th minus, or plus x to the what? 8th? Do you agree with that? But what is this? We know that this right here, so what did you do next? You know that this is, going backwards, the derivative of what? Our tan x, right? If you want to get rid of the derivative part of that, you have to do what? What operation? Integrate. You have to integrate. So if you integrate one side, what do you have to do to the other? So therefore, you know that tan inverse of x has to be the integral of this, which is going to be x plus, yep. Did I do it wrong? What did I do wrong?
It should be the 1 over x minus x should be 1 plus x squared plus x cubed. So
Oh yeah, you forgot the first.
1 minus x squared.
Oh, I forgot the x. Sorry, there's no 4 in there. Thank you. So what is that? That should be 1 plus x.
It's paused.
Thank you. Frozen? Yeah, thank you. So it should be 1 plus x. There's an x in there, right? So what is it going to be? 1 minus what? Thank you for that. 1 minus plus x to the 4th minus x to the 6th plus x to the 8th, right? So if you integrate these, you end up with negative x cubed over 3 plus x to the 5th over what? 5 minus x to the 7th over, etc. Does that make sense? So what do you have in your toolbox? You have massage it into something you know, substitute, and then you also can integrate or theoretically differentiate. Sometimes you might have to go down. Nice. So why is this helpful? It says use the series for arctan of x to determine the numeric value of pi.
X, you want to equal pi.
Yeah, so we want, exactly, we want tan inverse of x to be equal to pi, right?
Plug in for x whatever tan of pi is.
Yeah, so the thing about tan, yeah, so
Except what's the domain, what's the...
the hint I'll give you here, the hint, exactly, you have to watch out for the holes in the domain, right? The hint I'll give you is you could do any fraction of pi, right? You could do half of pi. So let's do that instead, okay? So like, let's make it, so you know, 2 times that is equal to some fraction. Let's say we want made it equal pi over 2. Correct? Is everybody okay with that? Sure. So if we did that, then we could estimate pi just by doubling it, right? So the tangent of what is pi over 2? Or do you want to do pi over? Do you want to do pi? We could pick any one we want that we know a nice tangent value of. Which one do you want to choose?
Pi over 4.
I like pi over 4 personally. It doesn't really matter in this case, but pi over 4 is great because it's definitely in the domain. The tangent of what is pi over 4? 1. Why did I choose that? Because you know that tangent of inverse of 1 is pi over 4. Do you agree with that? Yeah. So what do you know? 4 times tan inverse of 1 is equal to pi. So what do I plug into this? What do I plug in? 1. Look at this. Oh, it's over here.
Everything by 4.
And then you multiply what you get by 4. Exactly. Look. So what do we do here? Look. I'll make it a little bigger. So what do you end up with? You know, tan inverse of 1 is equal to, oh, look at that. So you plug in 1 to this. You plug in 1 to that. So that's a way to estimate pi, everybody. 4 times this is going to be an estimate for pi. You just came up with a way to estimate pi as accurately as you want. How do you make this more accurate? You just take more and more what? Terms. This actually approaches pi, which is really cool. So we just found another way to generate pi. So if you do that on your calculator, look what you get. 3.3, I had to do it out in several steps. 3.3033, it's a little bit higher. But what type of series is this? What type of series is that right there? Alternating, right? So it's going to be above pi, and then it's going to be below, above, below, above, below, above, below, above, below. Pretty cool, huh? 4 times that is equal to pi. So if you ever wanted to really accurately calculate pi, just go multiply by 4. Do you like my sound effects?
Yeah.
I think my sound effects are pretty good.
Put like the sum thing.
On like 14, okay? Hold on, this is important. Seema, you're gonna wanna pay attention to this. So on these right here, it looks a little challenging. It says expand the quantity about 0 in terms of the variable given. Give 4 non-zero terms here. So let's take a look at 14 for a second. What does that one look like? What does it look like?
1 over 1 minus x.
So you're trying to press it in 1 over 1 minus x, right? And it says do it in terms of x over 2. So what do you need to factor out of the denominator?
2.
So 1 over 2 plus x is equal to 1 over 2 times 1 plus what? X over 2. Do you agree with that? So that's the same thing as 1/2 times 1 over 1 plus x over 2. Do you agree with that? So what does this almost look like now? Does it almost look like something? Yeah, this is 1/2 times 1 over 1 minus what? Negative x over 2. So where do you plug in negative x over 2? So this is the same thing as 1/2 times the summation of 1 over 1 minus y, where y is equal to negative x over 2. So do you see what happened there? So then you can write out the expansion. What's 1 over 1? Oh, so it's going to be 1/2 1 plus y squared plus y cubed. But then what do you plug in for y? So 1 minus x over 2 plus x squared over 4 minus x cubed over 8. So that would be the answer right there. 1/2 times that thing. So you can do similar math for all of these right here. It's really cool. It's really, really, really cool. Okay, get out of here. Thank you for your attention.